Welcome to the deep dive. Today we're getting into something really fundamental in chemistry, isomers.
That's right.
You know, molecules that have the exact same atomic formula, the same list of ingredients, if you will, but they're put together differently.
Yeah, and those differences in arrangement, they lead to completely different properties. It's fascinating.
It really is. It's like the hidden language of molecules. And understanding it is pretty key to understanding, well, matter itself.
Absolutely. So this deep dive, our goal is really to give you a clear roadmap through the world of isomers. It might sound a bit daunting, but we want to hit those aha moments for you.
Okay, so where do we start? I know there are different types of isomers.
Right. The first big split is between structural isomers and stereoisomers.
Structural and stereo, got it.
Yeah.
Both have the same molecular formula, right? Same number of carbons, hydrogens, etc.
Exactly the same formula. The difference lies in how the atoms are actually connected, or how they're arranged in 3D space. That's the fundamental divide.
Okay, let's tackle the first type then. Structural isomers. What's the defining feature there?
Structural isomers, sometimes called constitutional isomers, same thing. They have the same molecular formula, so same atom, same molecular weight, but the atoms are connected in a fundamentally different order.
Different connectivity. Can you give an example?
Sure, a classic one is C-urio. This formula can represent butane, which is just a straight chain of 4 carbons.
Yeah.
Or it can be isobutane, technically methylpropane. We have 3 carbons in a chain and 1 branching off the middle.
Ah, okay. Same parts, zero, but a different skeleton. One's a line, one's more like a T-shape.
Precisely. Same atoms, just hooked up differently.
And I guess that difference in hookup isn't just theoretical. It actually changes how the molecule behaves.
Oh, absolutely. Big time.
Yeah.
Because the shape and bonding are different, structural isomers often have very different physical properties.
Like what?
Well, take our butane example. Normal butane boils around 0 degrees Celsius. Isobutane. It boils way down at -12 Celsius.
Wow, just from moving one carbon.
Yep. And it affects melting points, solubility, density, even smell or color in some cases. It all stems from that different connectivity.
It makes sense if you think about how the molecules pack together or interact. A long chain versus a compact ball, they'll behave differently.
Exactly. Intermolecular forces are different. And it goes beyond physical properties, too. It affects their chemical reactivity.
How so?
Well, reactivity often depends on functional groups, like an alcohol group and AOH and where they are on the molecule. Structural isomers might have the same functional group but in a different spot, or even different functional groups altogether, even with the same overall formula. This means they'll react differently in chemical reactions.
Okay, so structural isomers. Same formula, different connections leading to different physical and chemical properties. Straightforward enough. What about the other main category? Stereoisomers.
Right. Stereoisomers. Now, these guys have the same molecular formula and the same atomic connectivity. The atoms are linked up in the exact same order.
What's different then?
The difference is purely spatial. It's about how the atoms are arranged in 3-dimensional space relative to each other.
Ah, okay, so the blueprint is the same, but the 3D build is different.
You got it. Think of it like having the same sequence of beads on a string, but you can twist or arrange that string differently in space.
And does this category split further?
It does. Stereoisomers are broadly divided into conformational isomers and configurational isomers. Let's start with conformational.
Conformational. Sounds like they can change their conformation, their shape.
Exactly. Conformational isomers or conformers, sometimes rotamers, are different spatial arrangements of the same molecule that can interconvert just by rotating around single bonds, sigma bonds.
So no bonds break, it's just twisting.
Just twisting. Think about ethane, CHO. You can rotate one CH group relative to the other around that central carbon single bond. The energy needed for this rotation is usually pretty low, so at room temperature, these molecules are constantly twisting and flexing between different conformations.
So they're basically the same molecule, just in different poses.
That's a great way to put it. It's one molecule rapidly changing its shape. This is different from, say, double or triple bonds where rotation is restricted.
But is the twisting totally free, or are some poses preferred over others? I seem to remember something about strain.
Good point. No, it's not totally free. Some conformations are more stable, lower in energy than others due to molecular strain.
Strain?
Yeah, there are a couple of types. Torsional strain happens when bonds on adjacent atoms are aligned or eclipsed. Their electron clouds get too close and repel each other. Then there's steric strain, which is when bulky atoms or groups bump into each other because they're forced too close together in space.
So the molecule tries to twist into a shape that minimizes both types of strain, the most comfortable pose.
Exactly. It spends more time in lower energy conformations. And chemists have a way to visualize this, looking down the bond. It's called a Newman projection.
Okay, Newman projection, how does that work?
Imagine you're looking directly down a specific carbon-carbon single bond. The front carbon is shown as a dot with its bonds sticking out. The back carbon is a circle behind it, with its bonds coming off the edge of the circle.
Right, so you see how the groups on the front carbon line up or don't line up with the groups on the back carbon.
Precisely. It lets you see the dihedral angle between groups. When the groups are as far apart as possible, we call that a staggered conformation. That minimizes torsional strain.
And that's the most stable.
Generally, yes. Within staggered, there's anti, where the biggest groups are 180 degrees apart, usually the most stable. And there's gauche, where they're 60 degrees apart. Still staggered, but maybe a little steric strain if the groups are big.
And the opposite of staggered is?
Eclipsed. That's when the groups on the front and back carbons are aligned, lining up with each other. This has high torsional strain because the electron clouds are repelling each other.
So higher energy, less stable.
Right. And the worst case is totally eclipsed, where the largest groups are aligned right on top of each other, 0-degree angle. That's usually the highest energy point in the rotation.
Okay, so molecules flex and twist, preferring staggered over eclipsed conformations. Does this apply to rings too, like cyclohexane?
It does, but rings add another layer of complexity because the atoms are locked in a cycle. This introduces something called ring strain.
Ring strain.
Yeah.
Right, that's because the bond angles might be forced away from the ideal 109.5 degrees for carbon.
This is part of it, yes. That's angle strain. But ring strain also includes torsional strain from eclipsed bonds within the ring and non-bonded or steric strain, where parts of the ring might bump into each other.
And cyclohexane is the classic example because it finds a way to minimize all that.
Exactly. Cyclohexane is famous for its chair conformation. It's called a chair because, well, it kind of looks like one. In the chair form, the bond angles are nearly perfect, 109.5 degrees, so almost no angle strain. And all the bonds along the ring are staggered relative to their neighbors, minimizing torsional strain. It's remarkably stable.
But aren't there other shapes cyclohexane can adopt? Like a boat?
Yes, there's the boat conformation, but it's much less stable. It has significant torsional strain because bonds on opposite sides are eclipsed, and it has steric strain from what we call flagpole interactions, two hydrogens at either end pointing towards each other and bumping heads, basically.
Flagpoles. Okay. So the chair is heavily preferred.
Definitely. There's also a twist boat, sort of an intermediate, but the molecule spends most of its time in the chair form. And importantly, the chair can flip.
A chair flip, what happens then?
It's a process where one chair conformation converts into another chair conformation. When this happens, all the positions on the ring that were pointing straight up or down, called axial positions, become angled outwards, called equatorial positions, and vice versa.
Axial and equatorial. And why does that matter?
It matters a lot if there are substituents, groups other than hydrogen, on the ring. Bulky groups strongly prefer to be in the equatorial position.
Why is that?
Because in the axial position, a bulky group bumps into other axial hydrogens 2 carbons away. We call these 1003 diaxial interactions. It's steric strain. Putting the bulky group in the roomier equatorial position avoids this clash, making the molecule more stable.
Got it. Bulky groups go equatorial. And we also talk about cis and trans in rings, right?
Yes. If you have 2 substituents on a ring, cis means they're on the same face or side of the ring plane. Trans means they're on opposite faces.
Okay. So conformational isomers are all about rotation around single bonds, leading to different temporary shapes like staggered, eclipsed, or chairboat. Now, what about the other type of stereoisomers, configurational?
Right, configurational isomers. The key difference here is that you cannot interconvert these isomers just by rotating bonds. You have to actually break covalent bonds and reform them to change one into another.
So these are more locked in their 3D shape?
Exactly. They have a fixed spatial arrangement. And a major group within configurational isomers are optical isomers.
Optical isomers. They interact with light somehow?
They do. Specifically, they rotate the plane of plane polarized light. And this ability comes from a property called chirality.
Chirality. That's the handedness thing, right? Like our hands are mirror images, but you can't overlay them perfectly.
That's the perfect analogy. A molecule is chiral if it's non-superimposable on its mirror image, just like your left and right hands. No matter how you turn them, they don't match up exactly. Chiral molecules usually lack an internal plane of symmetry.
And what makes a molecule chiral? usually a specific type of atom.
The most common way is having a carbon atom bonded to 4 different groups or atoms. We call that carbon a chiral center or sometimes a stereocenter. If a molecule has one of these, it's usually chiral.
And if it is superimposable on its mirror image,
Then it's achiral. Achiral molecules often do have a plane of symmetry.
okay, so chirality is the key to optical activity. What are the types of configurational isomers related to this?
There are 2 main types we need to discuss: enantiomers and diastereomers, plus a special case called mesocompounds. Let's start with enantiomers.
Enantiomers, are these the direct mirror images? The left-hand and right-hand molecules?
Exactly. Enantiomers are pairs of molecules that are non-superimposable mirror images of each other. Same formula, same connectivity, but opposite configuration at every single chiral center in the molecule.
And their properties. They're almost identical, aren't they? Except for that light thing and how they interact with other chiral things.
You've nailed it. Enantiomers have identical melting points, boiling points, solubilities, densities. Pretty much all physical properties are the same in a non-chiral environment. Their reactivity with achiral regions is also identical.
But they differ how?
2 key ways.
Yeah.
First, they rotate plane polarized light by the exact same amount, but in opposite directions. One rotates it clockwise, we call that dextrorotatory, or plus, or sometimes dic. The mirror image rotates it counterclockwise, levorotatory, or L.
Same angle, opposite direction. What if you mix them 50-50?
Good question. An equal mixture of 2 enantiomers is called a racemic mixture or racemate. Because the rotations cancel each other out perfectly, a racemic mixture is optically inactive. It doesn't rotate light at all.
And that can be important biologically?
Hugely important. Often in biological systems, which are themselves chiral, only one enantiomer of a drug will fit the target receptor and have the desired effect. The other might be inactive or worse, cause harmful side effects. The thalidomide tragedy is a stark example of this.
Right, where one enantiomer helped morning sickness and the other caused birth defects. A devastating difference.
Absolutely. The second way enantiomers differ is in their interactions with other chiral molecules or environments. Think enzymes, receptors. They can distinguish between enantiomers.
Okay. And there's a way to quantify that light rotation, specific rotation.
Yes. Specific rotation and its standard measure. It's the observed rotation angle adjusted for concentration and the path length of the light through the sample measured at a specific temperature and wavelength. It allows us to compare different chiral compounds.
Got it. So enantiomers, non-superimposable mirror images. What about diastereomers?
Diastereomers are also configurational isomers, so locked shapes, not interconverting easily, but they are stereoisomers that are not mirror images of each other.
Not mirror images. How does that happen?
This requires a molecule to have 2 or more chiral centers. Diastereomers have different configurations at some, but not all, of those chiral centers.
Ah, okay. So maybe one chiral center is the same handedness in both molecules, but another chiral center is opposite.
Exactly. And because they aren't mirror images, diastereomers, unlike enantiomers, have different physical properties, different melting points, boiling points, solubilities. Everything can be different.
And different chemical properties, too.
Yes, different reactivity as well, even towards achiral reagents. This difference in properties is actually useful because it means you can often separate diastereomers using standard lab techniques like chromatography or crystallization, which you generally can't do easily with enantiomers.
Is there a rule for how many stereoisomers are possible?
There is. For a molecule within chiral centers, the maximum number of possible stereoisomers is 2 sub. This total includes pairs of enantiomers and sets of diastereomers.
Okay. And you mentioned earlier that cis-trans isomers are a type of diastereomer.
That's right. Cis-trans isomers, or geometric isomers, fit the definition. They arise from restricted rotation, usually around a double bond or in a ring. They have the same connectivity but different spatial arrangements. Cis, same side, trans, opposite side, for key groups. They are not mirror images of each other, and they definitely have different physical and chemical properties. So they are a subtype of diastereomers.
Makes sense. Okay, so we have enantiomers, mirror images, and diastereomers, not mirror images. What about those mesocompounds you mentioned?
Mesocompounds are a really interesting case. A mesocompound is a molecule that has chiral centers, but the molecule as a whole is a chiral.
How can it have chiral centers but be achiral overall? That sounds contradictory.
It does seem that way. It happens because the molecule possesses an internal plane of symmetry. Imagine drawing a mirror plane through the molecule. One half is the perfect mirror image of the other half.
So the handedness of one part of the molecule cancels out the handedness of the other part.
Precisely. The internal symmetry means the molecule is superimposable on its mirror image, making it achiral overall, despite having carbons with 4 different groups attached.
And if it's achiral, it doesn't rotate light.
Correct. Mesocompounds are optically inactive. Tartaric acid has stereoisomers that include a pair of enantiomers, which rotate light, and a mesocompound, which doesn't.
Okay, that clears up the types.
Right.
Now, how do we actually label these specific 3D arrangements? Like, how do we name the specific configuration?
Good question. We need ways to specify the exact 3D shape. We talk about relative configuration, just comparing one molecule to another, saying if they're enantiomers or diastereomers. But for the precise arrangement, we need absolute configuration.
And for that, we have systems like EZ and RS.
Exactly. The EZ system is primarily for describing the configuration around double bonds, especially when cis and trans become ambiguous because there are 3 or 4 different substituents.
Right. How does EZ work?
It uses the Coningold prelog or CIP priority rules. You look at each carbon of the double bonds separately and assign priorities, first, second, to the 2 groups attached to it. Priority is based mainly on the atomic number of the atom directly bonded. Higher atomic number gets higher priority.
Okay. Assign priorities on each side of the double bond. Then what?
Then you look at where the 2 highest priority groups are relative to the double bond. If they're on the same side, it's Z from the German zusammen, meaning together. If the highest priority groups are on opposite sides, it's E from entgegen, meaning opposite.
Z for same side, E for opposite. Got it. Okay, what about the R and S system? That's for chiral centers, right?
Yes, R and S. Define the absolute configuration at a single chiral center. It also uses the CIP priority rules. First step, assign priorities 1, highest, through 4, lowest, to the 4 different groups attached to the chiral carbon.
Same priority rules based on atomic number. Step 1, prioritize. What's step 2?
Step 2 is crucial. Orientation. You need to mentally view the molecule so that the lowest priority group, group 4, is pointing away from you, like into the page or behind the molecule, often shown with a dashed line or wedge.
Okay, put group 4 in the back then.
Step 3. Trace the path from priority group 1 to group 2 to group 3. Ignore group 4 now. If that path, 1 to 2 to 2 to 3, goes clockwise, the configuration is R for rectus, Latin for right. If the path goes counterclockwise, the configuration is S for sinister, Latin for left.
Clockwise is R, counterclockwise is S, after you put group 4 in the back. What if it's not pointing back in the drawing I'm looking at? What if group 4 is pointing out at me on a solid wedge?
Yeah, that happens a lot. Couple ways to handle it. One way, determine the R or S as if it were oriented correctly. Since group 4 is pointing the wrong way, toward you instead of away, the actual configuration is the opposite of what you just determined. So if you trace clockwise R, but group 4 is forward, the real answer is S.
So figure it out, then flip the answer if 4 is forward.
That's one quick way. Another method is to do a double swap. Swap group 4 with the group that is pointing back, then swap the other 2 groups. Doing 2 swaps gets group 4 back but retains the original configuration. Or you can just mentally rotate the molecule, whichever works best for you.
Needs a bit of 3D visualization. Do Fisher projections help here?
They can. Fisher projections are a 2D way to show 3D chiral molecules, especially useful for sugars and amino acids with multiple chiral centers. Remember, the horizontal lines are coming out at you, wedges, and the vertical lines are going back, dashes. The intersection is the chiral carbon.
Horizontal out, vertical back. Got it. How do you assign RS on those?
Well, ideally, you want the lowest priority group 4 on a vertical line, because that means it's pointing away. If it is on a vertical line, top or bottom, you just trace 1 of S, 2 of 3. Clockwise is R, counterclockwise is S, easy.
But what if group 4 is on a horizontal line, meaning it's pointing towards me?
Same trick as before applies. If group 4 is horizontal, coming towards you, trace 1 in S, 2 minus 3, as usual. Whatever answer you get, R or S, the true configuration is the opposite. So if you trace S, but group 4 was horizontal, the real answer is R.
Okay, so determine RS, then flip if group 4 is horizontal. Or you could do swaps on the Fisher projection too, I guess.
Yes, but you have to follow the rules. A 180-degree rotation of the whole projection keeps the configuration. A 90-degree rotation flips it. Swapping any 2 groups flips it. Swapping 2 pairs keeps it, so you can manipulate them to get group 4 vertical if you prefer.
Oh, wow. Okay, that really covers the landscape, doesn't it? From structural isomers just having different connections to stereoisomers having the same connections but different 3D shapes.
Right, and then stereoisomers, splitting into the flexible conformational ones, changing via bond rotation, and the rigid configurational ones. needing bond breaking to change.
Including enantiomers, those non-superimposable mirror images, diastereomers, which aren't mirror images, and those special mesocompounds with internal symmetry.
And finally, the systems like E, Z, and RS to give each unique spatial arrangement a specific name.
It really hammers home how important that 3D arrangement is. It's not just about what atoms are there, but exactly how they're positioned in space.
Absolutely critical. These subtle differences dictate everything from boiling points to, as we discussed, how drugs interact in our bodies. It's not just abstract theory, it has profound real-world consequences.
It really does. And it makes you think, doesn't it? How these tiny, tiny differences in molecular shape can lead to such huge differences in effect. Like, you mentioned drugs, but even something like smell.
Oh, definitely. Our sense of smell relies on odor molecules fitting into specific chiroreceptors in our noses. Sometimes two enantiomers can smell completely different because they fit into different receptors. One might smell like spearmint, and its mirror image smells like caraway seed.
That's amazing. Just a mirror image difference leads to a totally different perception. It really shows how much geometry matters at the molecular level, impacting our microscopic world and even our senses.
Precisely. So hopefully this deep dive has given you a clearer picture of the isomer landscape and why understanding these spatial relationships is so fundamental to chemistry and biology. It's a field where there's always more to discover.
Absolutely. Lots to think about there. Thanks for walking us through that complex world.